Hello and welcome to my third physics experiment for the year. This experiment is going to have two parts. For the first part, I'm going to play with density. I'm going to build a carefully crafted boat made of tinfoil, and I'm going to put it in a clear cup of water, or a clear tub of water, and I'm going to add a mass to it and see how far it can, or how much mass it's going to take for it to sink so that it goes to halfway under the water. For the second part, I'm going to play with density and fluids. For this part, I'm going to have a density tube or a thin glass, and I'm going to put different liquids like honey, water, syrup, things I can find around the house, and see which ones go to the bottom and which ones go to the top, and explain why the varying densities allow some to sink to the bottom and for some to the rise to the top. Okay, so I have my tinfoil boat with walls of 1 inch high, and I have a black line on each of the four sides marked at ½ inch, so I know when that ½ inch reaches the water line, it'll be halfway underwater. I have my tablespoon here, and I'm going to start adding sugar. So let's add our first tablespoon of sugar. There we go, it's one. And a little update after putting my sugar in. After 9 tablespoons of my sugar, I have put it in, and it is about halfway, or it is almost at that water mark. Okay, so for part 2 of this experiment, we'll be making my signature cocktail, my density cocktail, starting off with our maple syrup, then moving up to our dishwasher soap, and then going to our lemonade. So starting, we're gonna put the the maple syrup in the glass. We'll fill it up to right about there. You can see it sits at the bottom. And now we'll top it off with our syrup. And you can see these two blend. And as you look closely, that blue, the soap actually wants to fall below the maple syrup. But because they're so close in density, they're not gonna move too much or too quickly. And then we'll top it off with our lemonade. We'll pour it gently. And there you go. You can see that our lemonade, based on the way I poured it, it wants to go below that soap. But now that it's lighter in density, it's actually wanting to float to the top. So we can see at the very bottom, we have that syrup, and then the lemonade in the middle, and you can see that sort of circular motion as it makes its way to the top. And then at the top right now, the soap, which is slowly but surely falling back down to sit on top of the syrup, but below the lemonade. A few minutes later, and our density tube still looks like this, where the soap is on the top, and that lighter, less denser lemonade is in the middle with the syrup being on the bottom. And my one theory is that it's because the soap is hydrophobic, where it doesn't want to go below the high watery lemonade. It wants to stay on the top, on the surface. And so even though that it's more dense, it still doesn't want to blend in with that lemonade and go back down to the bottom. So the math behind the first part of the experiment, we have our boat in the water, and we have two forces acting on it. We have the buoyant force, and we have the actual weight, which is bringing it down. So we fill up, if you remember, about 9 tablespoons of sugar, which equals 37.5 grams or 0.0375 kilograms of weight added to the boat. So with this, we can add our mathematical equation. I measured that my boat is 4 inches by 3 inches, and we sunk it halfway, so ½ inch tall. With that, we get 6 inch cubed, and according to my search, 6 cubic inches of water will equal 0.016 kilograms of water. So that's how much water we displaced, or in other words, that's how much that's how much weight we added to make this boat sink halfway if we calculated it. However, we weighed something different. We weighed our 0.0375. So when we calculate our percent error, we get something rather big. We get a 78% error. Luckily, I remembered to measure the weight of the boat, which is 0.01 kilograms, and we add that to our already added weight, and we get 0.0475 kilograms. That is very close to our calculated weight of 0.048. Multiply that by 100, and we get a 2% error. Much better. Now we go over to our density tube, and you can see I drew a little diagram with the syrup being on the bottom, the lemonade in the middle, and the soap at the top, to my surprise. Now, to understand why it looks like this, we need to understand density. Density is just mass over volume. So when we look up and calculate the mass over volume of our three liquids, soap, lemonade, and syrup, we can see that soap is 1.06 grams per milliliter. Lemonade is 0.92 grams per milliliter. So you can see that lemonade is just slightly less dense than soap. So maybe that's why the lemonade didn't float to the top, even though it was lighter and less dense. It still was probably close enough to the soap that it didn't really need to move. And that's why we get those streaks of soap slowly going down, but in no hurry. And then that syrup is 1.37 grams per milliliter, much more dense, and it makes clear sense why it stayed at the bottom. So there you have it, another successful experiment showing buoyant forces, but also density of liquids. I think this was very accurate. We had very precise results with really good attempts and good math describing the physics that happened behind it. Stay tuned and I'll see you next time for the next experiment.